Hello, Takahashi-san. Hi.
Hi, can you hear me?
Yes, I can hear you.
Okay, I'm sorry for not being able to come this time. I'm very sorry for this.
Uh, sorry for the delay.
No problem, that's no problem. So can you see my screen and the cursor properly?
Yes,
Okay,
we can see your screen and also pointer.
okay, great.
Mm. So today and tomorrow we'll have a 2-hour lectures by Professor Fuminobu Takahashi at Tohoku University, and he will give a 2-hour lectures on actions in astrophysics and cosmology. Originally, he was supposed to come, but he has some problems, so he will give online lectures. Let's welcome Professor Takahashi.
Hi.
Yeah, so please you can start. Yes.
Okay. Okay. Thank you very much. First of all, I just thank the organizers for this opportunity, and also I apologize for not being able to come this time. In fact, I had a back injury last week, and it was difficult for me to get out of my bed for a couple of days. Now I recovered more or less. In any case, I'm happy to be able to give this lecture, albeit online. And today and tomorrow, I give lectures on axions. And today I will talk about various bounds on the axion couplings. And tomorrow I will talk about more specific topics. And I'm planning to talk about axion domain walls and the nanohertz gravitational waves, whose existence has been recently detected or hinted by the pulsar timing array data. Okay, today I'll talk about axion couplings. So why axions? Axion is a short number Gaussian boson associated with the spontaneous breakdown of some global continuous symmetries. So as the simplest example, let us consider U1 PQ symmetry. PQ stands for Pechai and Quinn, who propose a very nice solution to the strong CP problem. And when this U1 PQ symmetry gets spontaneously broken, axion appears along the phase direction, and they are massless if the U1 PQ symmetry is an exact symmetry. On the other hand, the radial mode, which is often called the axion, has a non-zero mass. Okay, and the interaction of the axion is suppressed by the decay constant Fa, and which is of the same order as the symmetry breaking scale in the relatively simple setup. So for instance, in this case, decay constant is of the same order as the VEV of the scalar field. But actually the relation between these two scales, decay constant and the symmetry breaking scale, is actually model dependent. And if you consider a complicated UV completion, such as the multiple PQ scalars with a certain charge assignment, then you can actually have exponential large hierarchy between these two scales. Today, I'm not going into details of that model, but tomorrow, if time permits, I will briefly mention that kind of possibility. And on the other hand, according to the quantum gravity theory, it is strongly believed that any continuous global symmetries must be broken explicitly. So if this is the case, this U1 PQ symmetry should be also broken explicitly. And as a result, the axion acquires a tiny mass, here denoted by MA. And the reason why the axion is important in cosmology or astrophysics is because its interaction is very weak and the mass is very light. So because the strength of interaction is suppressed by decay constant, so if Fa is large, its interaction must be very weak. And for instance, because the mass is light, interaction is weak, its lifetime can be easily much longer than the present age of the universe. So it implies that once produced, such axions would contribute to dark matter density. Also, it can be copiously produced inside the stars, and they carry away some energy affecting the evolution of the stars. Also, the mass is light. It means the potential is flat. So the axion can even drive inflation in the early universe. And if the mass is very light, it could also behave as dark energy, and so on and so forth. So I'd like to talk about those cosmological and astrophysical roles of the axion in this lecture. And probably you learn the QCD axion in other lectures by Professor Junjin Chun. So I quickly go through this subject. The QCD axion is one of the axions, and it was proposed as a solution to the strong CP problem. And the strong CP problem is why theta parameter, the coefficient of this operator is so small. So here, GS is the strong gauge coupling constant, G and G twiddle are the field strengths of gluons. And because it contains epsilon tensor, epsilon 0, 1, 2, 3, and it contains 0, the time component, this operator is odd on the time reversal, and it contains 3 spatial indices, 1, 2, 3, so it's odd under the parity transformation. So this operator breaks P and CP, but neither of which are symmetry of nature because they are broken explicitly by other standard model interactions. So we generally expect this operator with coefficient of order unity. However, it is known to be constrained to be less than 10 to minus 10 according to the neutron EDM bound. And this is a strong CP problem, and this can be solved by the Petrarch mechanism. And in this mechanism, this theta parameter is promoted to a field, axion field, and a phase decay constant. And this combination in the parentheses should be regarded as the effective theta parameter. Then the axion acquires mass from this coupling to gluons at a temperature lower than QCD scale. And this temperature dependent potentials are given by this equation. Here I wrote 1 minus cosine function, but this form is accurate at high temperatures, but in the low temperatures, this form is slightly different, but anyway, it doesn't affect the foreign argument. So I wrote it, I adopt a simple form, 1 minus cosine. And this prefactor chi of T is called topological susceptibility, and it is constant at lower temperatures, temperature lower than TQCD. TQCD is around 50 MeV. It's constant, but it's suppressed at high temperatures because QCD is asymptotic free theory. At high temperatures, it's perturbative, and such non-perturbative effects is very much suppressed. And this power C is given by 8.16 according to the lattice calculations. So you can see that at high temperatures, this axion potential is very much suppressed, but as temperature approaches the QCD scale, the axion potential quickly grows and becomes constant. So it's something like this. At high temperatures, axion potential is almost vanishing. It's flat like this. And as temperature approaches the QCD scale, it starts to grow and it becomes something like this. And the potential height is about the 100 MeV to the 4th power. And when this curvature of the potential becomes comparable to the Hubble parameter, the axion starts to oscillate about the minimum where CP is conserved. So the axion can dynamically solve the strong CP problem. But in the early universe, the potential is flat, so there's no reason to expect the axion sits exactly at the CP conserved minimum. So the axion is generically initially deviated from the potential minimum in the low energy. And not only the QCD axion, in general, axions can have various couplings to the standard model particles. Here I wrote again the axion coupling to gluons. This is kind of defining interaction for the QCD axion, but in general, axion can have this kind of interaction. Here, NDW, called the domainable number, is the color anomaly factor, which is integer, and this domainable number counts the physically distinct vacua. For instance, here I draw the axion potential. It has periodic potential like this, and if NDW domain wall number is equal to 3, we identify this vacuum with this vacuum. Okay, so these two vacuum are physically identical, but these two are not. Okay, or these two are not. So we have three distinct vacua. So this is a case for NDW equals to 3. And this capital FA corresponds to the wave of the scalar field in the simplest example on the previous slide. And NDW is actually depends on UV completion. So more precisely speaking, it is determined by the number of PQ quarks coupled to the PQ scalar. And in the QCD axiom, the decay constant FA is defined by this equation. Okay. So it is related to the domain wall number through this relation. And the QCD axiom can be classified, broadly classified to two classes or models. One is DFCD axiom, the other is KSVD axiom, depending on what colored particles run in the loop in this diagram, connecting the axiom to gluons. In the case of DFCD axiom, the ordinary quarks, standard model quarks, run in the loop. And because we have 6 different types of quarks, the domain wall number is either 3 or 6, depending on how you couple Higgs sector to the PQ scalar. And in the KSVD axiom model, which is much simpler than the DFCD axiom from model building point of view, the heavy unknown quarks run in the loop. Okay. So in addition to axion coupling to gluons, the axion can have various couplings to the other standard model particles, especially the coupling to photon is important from experimental point of view. And it is customary to express axion photon coupling in terms of GA gamma gamma defined by this interaction. And when expressed in terms of E and B, electric field and magnetic field, it is given by A, E dot B. And sometimes we call the axion coupled to photons as axion-like particle or ALP. And you can also write the GA gamma gamma in terms of the electromagnetic anomaly coefficient, C gamma. Again, this is a model-dependent parameter. In the case of QCD axiom, you also have contribution from the mixing between QCD axiom and mesons to this axion photon coupling. And unlike the axion coupling to gluons, this axion coupling to photons does not generate any mass for the axion unless there is magnetic monopole. If there are magnetic monopoles, the axion would acquire finite mass from the axion photon coupling. That's called the Witten effect. But I'm not talking about Witten effect in the rest of my lecture. But anyway, the axion also has interaction with fermions. Here I wrote the axion electron coupling. CE is a PQ charge of electron field, and the axion has a derivative coupling with electron field. And when you rotate the electron field, you can go to the another basis where instead of the derivative coupling, we have axion electron coupling in the mass term. So axion couples to electron mass like this. So in any case, at the low energy, this part, because it contains gamma 5, this part becomes the spin of electrons, and axion is coupled to spin of electron through this interaction. In the case of the DFCD axion model, the axion has tree level coupling to the electrons. And similarly, axion has a coupling, derivative coupling to nucleons like this. Here, capital N is either proton or neutron. Okay. And through these interactions, axions can be produced through various processes. And here I show some of the relevant production processes. And one is the Primakov process. Here I show the Compton process, and the other is the last one is Bremsstrahlung. So assuming the axion photon coupling G gamma gamma, you can write this kind of diagram. So here the electron or ions generates effective or external electric field or magnetic field. Then in the presence of the external electric field or magnetic field, photons are mixed with axions. So photons can be converted to axions, or vice versa, axion can be converted to photons. So this process is called Primakov process. And the next one is Compton scattering. And the usual Compton scattering is, of course, scattering between electrons and photons. But if we replace photon in the final state with axion, this process is also called Compton production process. And here we have GAEE, the axion electron coupling. Then the axion is produced through this Compton scattering process. The last one is the Bremsstrahlung. So the axion is produced through this Bremsstrahlung process of the scattering between electrons. You can also replace one of the electrons with nucleons, or you can replace both of electrons with nucleons. In that case, you also replace photon line with pion exchange. Okay. And you can constrain the axion electron coupling or axion nucleon coupling by considering the axion production from these processes. Okay. And there are other production processes of axions, but these are particularly important in hot plasma in the outer universe or inside stars. And this figure shows the current bound on axion photon coupling, GA gamma. It has a unit of the inverse mass. So this GV inverse, the horizontal axis, axion mass ranging from 10 to minus 12 eV to 10 kV. And these shaded regions are excluded by observations or experiments. This light shaded region shows the future prospect of the various experiments. Some of these exclusion assumes that the dark matter is made of axions. So axions constitute 100% of dark matter. For instance, this X-ray bound and this helioscope bound, they assume the axion is dark matter. And so you can see there are many observation bounds. And similarly, we have many bounds on the axion electron coupling and axion nuclear coupling like this. But due to the limited time and also my ability is limited, I cannot explain all of them. But instead, let me classify the existing bounds depending on where the axion is produced and how the axion is detected. And for instance, the axion may be produced at the ground-based experiments and they may be detected directly. For instance, this LSTW means the light shining through the wall experiment that uses laser, and using Primakov process, they produce axions from laser, and then again, through the inverse Primakov process, the axions are converted back to photons. They try to find this kind of signature, or the axion mediates some spin-dependent force. As I mentioned, axions coupled to spin of electrons, axion mediates a spin-dependent force. There's an experiment which is trying to search for this fifth force. Or inside stars, axion can be produced copiously, and there's solar axion site experiments. They're trying to detect axions, or this a little bit more indirect way, but it's very similar. That if axion is produced from the stars, it carries away some energy, and it affects the evolution of the stars, and it could even affect the lifetime of the star. And it's like paying tax, right? If the tax rate is very small, it doesn't affect our life, but if tax rate is very high, it could affect our life and even lifetime. So this is similar to paying taxes. And axion may be produced in the outer universe, and there's many experiments trying to look for the axion dark matter. Okay. And the axion could also affect the CMB and so on. So in the rest of my time, I tried to explain all these existing bounds. Okay, let me begin with production of axion dark matter. So as I mentioned earlier, in the early universe, axion is light, so it doesn't know where the minimum is. So it is generically deviated from the potential minimum by some amount. And here, the origin of A axion is said to be the potential minimum. So AI represents initial amplitude or initial position of the axion. Here, I'm assuming the so-called pre-inflation scenario where the U1 PQ symmetry is already broken during inflation, so that axion field is almost spatially homogeneous. Then the axion follows this equation motion, and here I approximated potential by the simple mass term. MA is mass of the axion. Then in the very early universe, hyperparameter is large, mass is small, so the axion field does not move due to this frictional force proportional to hyperparameter. But as time goes, the hyperparameter decreases, and when it becomes comparable to the mass, axion field's potential and start to oscillate about potential minimum. And afterwards, this hyperfrictional force can be neglected. Then you can see that the equation of motion the axion follows is just a simple harmonic oscillator. So axion starts oscillate. And this oscillation energy explains dark matter. In the case of QCD axion, the potential height is fixed to be QCD scale. So the mass and decay constant are related to each other. So you can express the axion density in terms of only decay constant Fa. And this finite power comes from the temperature dependence of the potential. And theta I is the initial misalignment angle defined by AI over Fa. The most natural value of theta I is over the unity. And capital F of theta I is a so-called anharmonic effect. And if the potential is deviated significantly from the quadratic potential, you have to multiply this correction factor. So typically, if you put the axion close to the top of the potential, the onset of oscillation is delayed, which enhances the final axion abundance. And this effect is encoded in this function. So you can see from this expression, in order to explain all the dark matter density by the QC, this misaligned mechanism, Fa should be around 10 to 12 GeV for theta I over the unity. Okay. So this sets an upper bound of the so-called classic axion window. Fa should be in this range. If Fa is greater than 10 to 12 GeV, you need to fine-tune the value of theta I much smaller than unity to explain the dark matter density. On the other hand, lower bound on the axion decay constant comes from the stellar cooling argument, such as neutron stars, and also the similar bound comes from the supernova 1987A. And the typical mass of the QCD axion to explain all dark matter is around micro eV, as you can see from this equation. So this is from the misalignment mechanism. The axions can also be produced from the decay of topological defects, cosmic strings, and domain walls. So here I'm considering the post-inflation scenario where U1 PQ symmetry gets broken after inflation. Then associated with this phase transition, cosmic strings are formed. So inside cosmic strings, the PQ scalar field sits at the origin where the PQ symmetry is restored. Okay, and so this cosmic string is formed associated with the U1 PQ symmetry. Gets supposed to break down of this U1 PQ symmetry, and they evolve in the expanding universe. And there are many works that solve the equation motion for cosmic strings on the lattice calculation. And I took the numerical result from this paper that appeared 2 years ago. And here, this yellowish object is the cosmic string. And this bluish, the region shows the axion energy density. And this red box represents the hub volume at this moment. And you can see that a few cosmic strings are contained in the hub volume. And this situation is called scaling solution. So the evolution of cosmic string is something like this. So first, the cosmic strings are formed when the U1 peak symmetry gets broken. Then the cosmic strings will move around at the speed close to the speed of light. And when they meet, they reconnect and they try to minimize their length, total length. And in a few Hubble times, it is known to follow the so-called scaling solution, where on average, order 1 cosmic strings are contained in each Hubble volume. Then, when the temperature decreases and becomes comparable to the QCD scale, the axion feels mass. Okay. And it starts to oscillate, and the domain walls are formed. And each, as you can see from this figure, these bluish region represents domain walls. So they are bounded by cosmic strings. And due to the tension of domain walls, those strings are attracted to each other. And when they meet, they annihilate. So the string wall network annihilate when domain walls appear around the QCD phase transition. So by the way, this is a case of the domain wall number equal to unity. So in this case, there's unique vacuum. So domain wall network annihilate and disappears. If domain wall number is greater than 1, say equal to 2 or 3, then string wall network is stable, and you have to make this string wall network unstable. Otherwise, it will be inconsistent with observations. However, according to the recent numerical calculations, it was found that there is some deviation from the scaling solution. The more precisely speaking, the number of cosmic strings contained each Hubble horizon grows logarithmically, and we don't know why this happens. There's a couple of reasons proposed so far. It may be related to the tension of the global strings, and because the tension of global string is known to grow logarithmically, so maybe related to this the logarithm growth of the tension. But anyway, we don't know the exact reason why this is the case. And also in the numerical calculation, you cannot simulate the realistic values because in the realistic situation, you have huge hierarchy between the QCD scale and the PQ breaking scale, and this cannot be simulated on the lattice. So you need some extrapolation to estimate how many axions are produced from the cosmic strings. And depending on how you extrapolate, the result changes. And at this moment, there's no consensus about the string contribution to the axion dark matter density. So the value of the axion decay constant for this axion produced from string wall network to explain all dark matter is probably between the 10 to 9 or 10 to 11 GeV, but we don't know the exact value yet. Okay, so let me go on to the next topic, axion ice curvature perturbations. So like the inflaton, axion also acquires quantum fluctuations, delta A, whose size is given by the Hubble parameter during inflation, H inflation. So, and here I'm assuming the pre-inflation scenario where your peak symmetry gets already broken during inflation. So the axion exists during inflation. And because it's light, it acquires a quantum fluctuation like this. And it means that the axion starts to oscillate with a slightly different amplitude from point to point in space. And this fluctuation in the axion density has nothing to do with the inflaton's quantum fluctuation that generates the so-called adiabatic perturbation or density perturbation we observe today. So this independent fluctuation in dark matter density can be distinguished from adiabatic density, density perturbations, and it's called ice curvature perturbations. And it's quite easy to estimate this ice curvature perturbation S. It is defined by the density fluctuation in the axion density divided by the total dark matter density. Here inserted the omega A, the density parameter for the axion in the numerator and denominator this way. And noting that axion density or axion abundance is proportional to initial amplitude squared, because the oscillation energy becomes dark matter, so its energy is proportional to the amplitude squared. So you can calculate this part like this. You get delta theta over theta, and with a factor 2 comes from theta squared. And substituting the delta theta I equals to a proportion to hyperparameter, you get this result. So the axion ice curvature perturbation depends on the fraction of the axion dark matter and the inflation scale and the decay constant. So we have two different kinds of fluctuations. One is adiabatic perturbation, denoted by R. The other is ice curvature perturbation, denoted by S. The adiabatic perturbation is generated by the fluctuation of the infraton. And what the quantum fluctuation of the infraton does is to perturb the evolution of the universe from point to point in space. And this can be understood as follows. So infraton is slowly rolling on top of the very flat potential during inflation. So suppose that the axion starts from here and rolls down to this direction, let's say to right direction. Then on top of this classical motion, it acquires quantum fluctuations. If the direction of quantum fluctuation is same as the classical motion, then in this case, inflation ends earlier than the average. On the other hand, if the direction of the quantum fluctuation is opposite to the classical motion, then the inflation lasts longer than the average. So what the quantum fluctuation of the infraton does is just to perturb the evolution of the universe. In other words, it generates the fluctuation in the cosmic time. And after inflation, photon or dark matter or baryon, their energy density decreases with time. It's proportional to some inverse power of scale factor, and because the universe is expanding, it's a decreasing function of time. And now the cosmic time is fluctuating due to the quantum fluctuation of the infraton. Photon or the dark matter energy densities also fluctuate, but they fluctuate in the same way, okay, because it is time that is fluctuating. On the other hand, ice curvature perturbation, for instance, if you consider radiation dominated era, there's no perturbation at all in the radiation energy density, only dark matter fluctuates. So the ice curvature perturbation is a relative fluctuation between different components. Okay. And these two the fluctuations can be distinguished, and we have a very tight constraint on ice curvature perturbations. In terms of the power spectrum, the ice curvature perturbation must be less than 10 to minus 3 of the adiabatic perturbations. And the reason why we can distinguish these two are because they appear in the CMB temperature power spectrum in quite different way. So this is adiabatic perturbation. This is what you usually see in the CMB temperature power spectrum. And the lower one represents ice curvature perturbation. And the ice curvature perturbation gets suppressed at the small scales because these modes enters much earlier, and when the ice curvature perturbation is relatively small, because dark matter density grows with time, because its energy density decreases more slowly than radiation. At early times, the ice curvature perturbation has little effect on the metric perturbation. And that is why ice curvature perturbation gets suppressed at small scales. And also the peak position is different. And this is can be easily understood as follows. When CMB photons are generated, the universe was dominated by dark matter. And dark matter also has fluctuations, adiabatic fluctuations. And where dark matter density is larger than the average, then we have gravitational potential well. Okay? And on top of this gravitational potential well generated by dark matter, we have baryon photon fluid, more precisely speaking, photon, protons, and electrons are combined through electromagnetic interactions. And these components behave as single component fluid, the compressed fluid, because photon has pressure. And then the mode enters the horizon. It realizes that it is actually fluctuation, not constant, and it falls down toward the potential minimum or gravitational potential well generated by dark matter. And because then gets compressed, but photons has pressure, at a certain point, it pushes back. And so it continues to expand and compress and expand and so on. So this is the so-called baryon-acoustic oscillations. It's a bit complicated to write down the exact the equation motion for this baryonic fluid, but essence is the same as simple harmonic oscillator. If you forget about cosmic expansion and so on, it's nothing but the simple harmonic oscillator. And as you know, there's two independent solutions to the simple harmonic oscillator, cosine omega t and sine omega t. And adiabatic fluctuation corresponds to cosine omega t, and ice curvature perturbation corresponds to sine omega t. Okay? The reason why ice curvature perturbation is given by sine omega t is that it grows with time. Okay? The dark matter density grows with time, so its effect on the metric perturbation grows with time. So that's why it's sine omega t. In the case of adiabatic perturbation, it's cosine omega t because the gravitational potential at superhorizon scale is constant. So that's why it's given by cosine omega t. And because it's cosine, the other is sine, peak location is different, you can distinguish these two different kinds of perturbations. And because ice curvature perturbations is given by a function of axion decay constant, Hubble parameter during inflation, so you can constrain the inflation Hubble parameter as a function of the decay constant. Okay. So this line corresponds to the upper bound on the Hubble parameter if we assume axiom explains all dark matter density. Okay. So you can see that the Hubble parameter cannot be greater than 10 to the 7th or 10 to the 8th GeV. It must be really small. For instance, the many hybrid inflation model or the Sierpinski type inflation model is not consistent with this bound. Okay. And as you go to smaller values of decay constant, in order to explain all dark matter density by this axiom, you have to put the initial position of the axiom close to top of the potential. Okay. Then the onset of oscillation is delayed, the abundance is enhanced. However, in this case, the final abundance becomes very sensitive to the initial position, and it implies that ice curvature perturbation gets significantly enhanced in this limit. So that's why the upper bound on the Hubble parameter becomes very tight in this limit. And this is due to a harmonic effect. Okay. So let me go on to the axion photon conversion. So as I mentioned, in the presence of axion photon coupling, the axion can be converted to photons or photons can be converted to axions. So this interaction can be written as AE.B electric field and magnetic field. If we replace one of these, say magnetic field with external field, you can see that axion and photon get mixed. Okay. And this is called the Primakov effect, and it is widely used in various experiments and observations. One example is a solar axion search experiment. Here I took figure from the KIAS collaboration, and inside the sun, the axion is produced from the Primakov process. So here we use electrons or ions that generate external electric field, and the photons are converted to axions, and axions propagate toward the Earth, enters this magnet bore, and here we have magnetic fields this direction, and the axions, some of the axions are converted back to photons. And axions are produced around the center of the sun, which is very hot, and the typical energy is around keV. So the converted photons have is an X-ray. And so they try to look for X-rays converted back to inside this magnet field. Okay. That's the solar axion search experiment. And similarly, the light shine through wall experiment uses laser. And so they use laser, which is directed toward the wall. And this laser cannot pass through the walls. It stops here. And they apply magnetic fields in front of this wall. And then some of the photons is converted to axions. Axions can easily penetrate the walls because it's very weakly attracted. And on the other side of the wall, you apply magnetic field again. Then some of the axions may be converted back to photon. They try to look for this photon. Or you can look for the effect of the gamma ray spectrum after the production of axions. So in the universe, there are sources that generates high energy gamma rays like AGN. So they emit high energy gamma rays. And when on the way to the Earth, it passes through the region where the magnetic field exists. And if the energy of photons satisfies certain condition, the photons get maximally mixed with axions. So the photon axion conversion takes place. But this conversion rate and also the energy of these photons depends on the various parameters, especially the direction of the magnetic fields between the source and the Earth, and also morphology of this magnetic field. And in general, the direction and morphology are random, so we expect some irregularities to exist in the gamma ray spectrum. So there are several people who look for such irregularities in the gamma ray spectrum of the several gamma ray sources observed by Fermi or Hess, and they constrain the axion photon coupling for a certain range of the mass. And you can also, so far the axions are really produced as real particles, but the axion may be produced virtually if the energy is very low, but still it could affect the refractive index of photons. So it could, the polarization of photons could be rotated and so on. It's called birefringence effect. And there are experiments that look for some special effect on the refractive index due to the presence of axions. So I took this figure from OVA experiment, and there's also a similar experiment called PB-LAS experiment, looking for this effect. Also, this axion photon conversion is exploited by various axion dark matter search experiments. For instance, ADMX, CAP, this Korean experiment, and Haystack. These experiments use the cylindrical the cavity, and where they have a strong magnetic field generated by a superconducting magnet. And the axion dark matter can be thought of as the oscillating classical background. It has the wavelengths much larger than the size of the detector, so it can be thought of as spatially homogeneous time oscillating classical background. Okay. In this case, you have effective electric field along the magnetic field, and this generates the time oscillating electric field, and this can be searched for by these experiments, and they typically use the resonance to enhance the signal. Okay. And this the resonant frequency can be adjusted by is determined by the geometry of the detector, and for instance, by inserting a certain rod into this detector, they can tune this resonant frequency to search for the axion dark matter for some range of masses. Okay, so I explained a couple of the other bounds shown in this figure. One is KIAS experiment, this KIAS bound comes from the solar axion search experiments, and the light shining through the wall type experiment is ALPS or ALPS2 experiment. They exclude this region, and the haloscope, ADMX or CAP, those experiments exclude these regions, and Fermi and Hess, the gamma ray spectrum irregularities, exclude these parameter space. But you can see that there are still lots of parameter space which are not explored yet, but in the near future, those huge parameter space will be explored. In particular, although not shown here, even in the very light axion mass range, there's also very interesting the effect known as causing birefringence. So as I said, this phi FL dual coupling is written as phi E dot B, and the ordinary Kernighan term for photons, F mu nu, when expressed in terms of E and B, is given by E squared minus B squared. Okay, so when axial field changes with time, so suppose that it is initially 0, and as time goes, it becomes non-zero, for instance. Then you have the mixing between E and B induced by this axial field. But this mixing can be absorbed by mixing E by defining this quantity. If you regard this quantity as new electric field, you can absorb this mixing part. In other words, when axion moves, the electric field and magnetic field gets mixed, and the polarization vector is defined to be the electric field. So polarization gets rotated as phi moves, and this is known as causing birefringence, and this occurs to the CMB photon. And there's some experiment like the bicep and KEK2. I took this figure from the bicep KEK2 paper. They looked for the temporal oscillation of CMB polarization due to the axion dark matter. The axion is oscillating in time. As I said, axion dark matter is just oscillation energy. And especially if you consider light mass, the amplitude is large because mass times amplitude is fixed for given axion density. So if you consider very light mass, like 10 to the minus 21 eV, then the amplitude is large, so the CMB polarization could rotate and oscillate with measurable amount. And they constrain this region. The region above this blue line is excluded by this experiment. Okay, so CMB polarization experiment can now look for axion dark matter through this technique. Okay, so I think I explained most of them. This one, solar axion, axion dark matter, and some spectral irregularities. And now I go on to the other spin-dependent force. So as I mentioned, axion is coupled to spin of electrons. So axion mediates spin-dependent force, generates spin-dependent force. So let's consider this simple model. Phi is axion, and it is coupled to fermion psi. And because axion is a pseudoscalar, it is coupled to psi over gamma phi psi, and this coupling is denoted by G sub P. And if you allow parity or CP violation, you could also write down the ordinary Yukawa coupling, and its coupling is denoted by G sub S. And this Feynman diagram represents the dipole potential, actually, because we use the GP and GP for both vertices. If we place one num GP with ordinary Yukawa coupling, you get monopole dipole potential. And this is what the Ariadne experiment is looking for. And by the way, if you place both vertices with Yukawa coupling, then you get the ordinary Yukawa potential. But here, let me focus on the dipole potential induced by this the Feynman diagram. Okay. And after simple calculation, you get this dipole potential given like this. And S1 and S2 represent the spin of fermion psi1 and psi2. And it is inversely proportional to R cubed. R represents the distance between the two fermions. So it decreases very fast as R becomes large. And it depends on the spins like this. Probably you have seen this dipole-dipole potential in the electromagnetism. So although it is slight digression, let me ask a question. Which sign is correct? Plus or minus? The sign is physical because this determines whether the potential is attractive or repulsive. So in principle, experiments can determine this sign. So this is physical. And if you are asked by such question, then probably the first thing you do is to check the literature. And this is the result. And as you can see, most of the papers, including the seminar paper by Moody and Richek, who studied this kind of potential for the first time, I believe. And there are also many theory papers, many experimental papers, which look for this dipole-dipole potential, said plus sign is correct. The review article says this is plus sign is correct. Even particle data group says plus sign is correct. And I found one theory paper which said minus sign is correct. It is this paper, but for some reason, they did not compare their result with the other literatures. Probably because they studied the various the potential induced by light mediating particles, and this is just one of the models they considered, and they did not make any comparison. By the way, if this were experimental data, I would choose plus sign without a shadow of doubt. And I may even start writing a paper suggesting plus sign. I'm joking, but anyway, this is just simple calculation, even the theorists can check. And so I calculated by myself, and I got minus sign. But I was not 100% sure if I was right, but I came up with a very good idea to check this result. I asked my graduate student to check the sign. And he got first plus sign, but I asked him to do it again, then he got minus sign. And we wrote a paper that minus sign is correct. So also, as a member of particle data group, I also corrected the sign error in particle data group. So it should be correct after 2018 edition. As a byproduct, we found the sign alternating rule depending on the spin of mediating particle. Okay, so in the lecture of electromagnetism, you know that dipole-dipole potential is energetically favored if the direction of spin is opposite. Okay, if the spins are located like this, maybe I should go to the next slide. So this is a configuration that minimizes the energy. So probably you know this in the electromagnetism. But in the case of axion exchange, the sign of the potential different. It means that aligned spins is energetically favored. And I also found that this is a case for the graviton exchange. Okay. And it is well known that the force mediated by scalar, just Yukawa potential, is attractive, and the force mediated by spin one particle like photon is repulsive between like charges, and the force mediated by spin two particle graviton is of course attractive. But we found that this same sign alternating rule also holds for spin dependent potential. And that was not noticed until our paper. Okay, so lastly, let me go on to the stellar cooling due to the axion emission. Because axion is very weakly coupled, once produced inside stars, it simply escapes from the star, carrying away the energy. Okay? And if takes too much energy away from the star, it affects the evolution of the stars. So you can constrain the axion coupling, or you may be able to get a hint for the extra cooling due to the axion. What I draw here is a horizontal branch star where the helium core is burning. And in this, by using the horizontal branch star, you can constrain axion photon coupling. So let me explain that in the rest of the book. This is famous HR diagram, and the x-axis denotes the surface temperature. So this is high, this is low, or it corresponds to color or spectral type. And the vertical axis is luminosity, or the brightness of this star. The gray band represents main sequence star, where the hydrogen is burning at the center of the star. So all the stars are main sequence stars at birth. And the nearest main sequence star is, of course, the sun, and inside which hydrogen is burning. But in several billions of years, the hydrogen is depleted at the center, and instead helium core grows, and then it gradually deviates from main sequence star and moves upward to the red giant branch. And as I mentioned, from the sun, we have the axion photon. We can constrain axion photon coupling through the solar axion. Such experiments, and we have upper bound like this. This is from KIAS collaboration. And when the main sequence star, like the sun, becomes red giant, you can constrain the axion electron coupling. And this, to derive this bound, you use the so-called tip of red giant branch. Let me explain a little bit more. So the helium core is inert until it ignites, and around the helium core, hydrogen is still burning in the shell, and as the more hydrogen burns, the more helium is supplied, and helium core glows. But because there's no heat source inside helium core, it cannot support gravitational force, so it contracts. And because of the gravitational potential, it becomes heated, but still there's no heat source, so it continues to shrink until it gets supported by the degenerate pressure of electrons. And for the main sequence, the Roma star with mass lower than twice the solar mass, the helium core with supported by degenerate pressure is realized. And what is nice about this degenerate pressure is that it doesn't depend on temperature. So there's no kind of back reaction on the temperature. In usual star, where the thermal pressure is dominant, if the temperature increases for some reason, it expands because thermal pressure increases, volume expands, so the temperature drops, and it regulates nuclear reaction rate. However, in the case of degenerate pressure, if for some reason temperature increases, there's no way to regulate the temperature or the nuclear fusion rate. And at a certain point, when the mass of helium core reaches a certain value, it ignites through the so-called triple alpha process. 3 helium nuclei fuse into carbon nucleus, and then heat is generated. But because it is supported by degenerate pressure, temperature doesn't just increases because volume does not expand. So temperature increases, but if temperature increases, this triple alpha process occurs more efficiently. The more heat is generated, so it leads to runaway nuclear fusion process, and it's called helium flash, and it suddenly jumped to the so-called horizontal branch star, which is much dimmer than the red giant, and this leaves the distinct discontinuity in this evolution, and you can see that tip of the red giant branch, where the red giant star is the brightest. Okay. And you can measure this tip of red giant branch and compare it to the theoretical prediction based on the stellar evolution. And you can constrain the axion electron coupling, because if axion is emitted from the helium core through the bremsstrahlung, so here I'm assuming axion is coupled to electrons, and the electrons can scatter by nucleon. And the electrons are degenerate, but the nucleons are not. So nucleons can scatter off the electrons, and if you attach axion in the final state, the axion can be produced. And then if axions are produced, helium core is cooled down, So the ignition of helium core is delayed, and this tip of red giant branch moves upward, so it gets even brighter. So by comparing with observations, you can put upper bound on axion electron coupling, and they get this value around 10 to minus 13. And after the helium core ignites, it jumps to the horizontal branch star, and similarly to the sun, through the Primakov process, the axion is produced from the helium core. Then as axion carries away energy, the helium core gets even hotter, and as a result, the triple alpha process occurs more efficiently, and the lifetime of horizontal branch star becomes shorter. So the number of horizontal branch star decreases by this effect. So they obtain this upper bound, and they also, at the end of the day, the star ends up with the white dwarf, and the white dwarf is a relatively simple structure. There's no heat source. Its cooling process is relatively well understood. You can compare the theoretical prediction of luminosity function, namely number density of white dwarfs as a function of their luminosity, and with with observations, and you can also include this axion emission from white dwarf in the code of numerical code of that solves the evolution of white dwarfs, and you can calculate the effect of axion emission on the luminosity function and compare it with observation. They get this upper bound, which is comparable to the one derived from red giant branch. Okay, so I think I spent most time, I believe, and I explained, I guess not all of them, but I explained most of the existing bounds shown in this table. So let me wrap up my talk. So axion has a very light mass, and its interaction is suppressed by decay constant. So if decay constant large, its interaction is very weak. So axion is naturally long-lived, and it's good candidate for dark matter. And what is particularly nice about axion dark matter is that its production process, or production mechanism, is built in. Namely, the misalignment mechanism can generate the axion. Okay. And also, as we have seen, the axion can have various couplings to the standard model particles like photon, electron, and nucleons. And among them, the axion photon coupling has been the most widely explored and therefore severely restricted. And it affects various things like stellar evolution, and also it could affect the spectral irregularities, and so on and so forth. And the axion dark matter can also be searched for by using these axion photon couplers. Okay, so that's all what I have to say. So thank you very much for your attention.
Okay, thank you very much. So, hello.
Hello, can you hear me?
Yes.
Okay.
Now it's time to start. I can see your screen, and okay, this is the second lectures by Professor Takahashi from Tohoku University. He'll talk about actions in astrophysics and cosmology. Please start.
Okay, so today, as I promised yesterday, I will talk about the gravitational waves generated by axion domain walls. But before starting to talk about these gravitational waves, let me answer the yesterday's question. So I'm sorry that I could not understand the question yesterday, but the question was, if I understand correctly, the spin-spin interaction or the dipole-dipole potential I derived yesterday is attractive for certain configuration of spins. So because it is attractive, is there any Sommerfeld effect? Probably that is the question asked yesterday. And the answer is yes, probably. And so I've not thought about the spin-dependent Sommerfeld enhancement factor, but if you consider scattering between the polarized fermions, and if this potential mediated by axion is dominant over the other interactions, then this could, in principle, lead to the Sommerfeld enhancement. However, in contrast to the ordinary Zoma field enhancement, the calculation is a bit more complicated because of the 1 over R cubed factor that appears in the spin-spin potential. So if you remember the formula, the potential is proportional to 1 over R cubed, so it becomes very strong at the short distance scales. But because of this very rapid the growth, this makes the ordinary Schrödinger equation ill-defined. So in the Zoma field enhancement, when you calculate the Zoma field enhancement, you need to evaluate the so-called ladder diagram, where the two fermions exchange, in this case, axions many times. So this represents the non-productivity effect associated with the bound state. And in order to evaluate this kind of ladder diagram, typically you solve the Schrödinger equation. But in the case of this 1 over R cubed potential, you have the bound state with arbitrarily low energy. So Hamiltonian in this case is not bounded to be low. So you have to somehow modify the theory. Namely, you need to cut off this 1 over R cubed potential by modifying the theory, like adding the contact term like 4 Fermi interactions. Then you can calculate the Zoma field enhancement by solving the Schrödinger equation as usual. And last night I found a nice paper that exactly studied this subject. So if you're interested in this topic, probably better to look at this reference. I hope this answers the question yesterday. Okay. So originally I was planning to talk about causing birefringence, but as you might have heard, last month the new data that came out from NanoHealth, the nanograph and other pulsar timing array collaborations. So I will talk about this gravitational wave production from axion domain walls. So probably I don't think I have time to talk about causing birefringence. But this is interesting topic. So if you're interested, please look at these papers. There's currently 3 sigma hint for the non-zero isotropic causing birefringence, namely the rotation of semi-polarization. And this can be nicely explained by the axion domain walls. I will talk about the first topic. So let me first review domain walls and cosmic strings. As I explained yesterday, the strings and domain walls are formed in the axion cosmology. So when U1 PQ symmetry gets spontaneously broken, cosmic strings appear. So this yellowish object is a cosmic string. And they quickly follow the scaling solution apart from possible logarithmic deviation. And then when the temperature becomes comparable to the QCD scale, the axion acquires mass and the domain walls appear. Okay. And so with the boundary given by the strings. And for instance, this is a snapshot of domain wall configuration in the case of domain wall number equal to 2. So you can see that domain wall like object with different color. So this different color represents different type of domain walls because we have the 2 domain wall or 2 vacua. So we have 2 different domain walls connecting the 2 vacua. Okay. And these objects are stable because we have 2 degenerate vacua, and so the string wall system remains stable. If domain wall number is equal to unity, because we have unique vacuum, wall and string decay and disappear. So this shows the potential in the case of domain wall number equal to 4. You can see that there are 4 distinct vacua. Okay, and in this talk, I'm interested in the stable walls. So if there's strings, we assume the domain wall number greater than or equal to 2. But you can also consider domain walls without strings. For instance, if axion is fluctuating around the top of the potential like this, then at one point in space, it may roll down to the right vacuum. In another place, it may roll down to the left vacuum. As long as both vacua are populated in space, the domain walls appear separating these two vacua. Okay? The fluctuation of the axion could be thermal fluctuations, or it can be the quantum fluctuation generated during inflation. And here I show a snapshot of domain walls simulated on a 2D space. And you can see that the two vacua denoted by two different colors are populated in space, and the domain walls are these boundaries between the two vacua. Okay. And once produced, like strings, domain walls are also known to follow the so-called scaling solution, where on average, one or two domain walls are contained in the Hubble volume. Then, if the domain wall network follows this scaling solution, the energy density of domain walls is given by tension sigma times Hubble parameter. So raw domain wall, of course, should be interpreted as the spatially averaged energy density of domain walls, because domain walls are localized object. So in the case of radiation-dominated universe, Hubble parameter decreases as A to -2. A is a scale factor. So energy density of domain walls decreases very slowly. In particular, compared to radiation, which scales at 8 to -4, or matter, which scales at 8 to -3, the energy density of domain walls decreases more slowly. So at the end of the day, it comes to dominate the universe. Okay. However, domain walls are spatially localized object. If it comes to dominate the universe will be completely inhomogeneous and anisotropic, and which is not consistent with our observations. So domain walls should not dominate the universe. And moreover, even if they are subdominant, it could generate metric perturbations. So in order to be consistent with the current CMB observations, stable energy density of stable domain walls is bounded above like this. It must be 10 to -5. It must be less than 10 to -5 of total energy density of the universe. And this leads to the upper bound on the tension, MeV cubed. So this is a really tight constraint. And if the tension of domain walls does not satisfy this upper bound, it should decay in the history of the universe. So we somehow make the domain wall network unstable. And one way to make the domain walls unstable is to introduce the potential bias. Namely, you need to lift the degeneracy between these two vacua. So here I consider the Z2 type Z2 domain walls, where originally we have Z2 symmetry, and as a spontaneous breakdown of Z2 symmetry, we have domain walls connecting this vacua to this vacua. But if we lift the degeneracy by adding some potential, namely by adding this potential of the autofunction given by autofunction of phi, you can lift the degeneracy of this vacuum. And now this the right vacuum becomes false vacuum, and this left vacuum becomes the true vacuum. So the region of the false vacuum feel pressure because there's cosmological constant in the false vacuum. It feels that it has negative pressure. So domain walls are, of course, separating these two vacua feels experiences force toward the false vacuum because of the negative pressure inside this domain. So domain walls get feels attractive force to each other. Then in the end of the day, it will collide and annihilate. Okay. So the question is when the domain walls start to annihilate. And there are two forces acting on the wall. One is the tension. Okay? And tension makes the domain walls as flat as possible because the energy of domain walls is proportional to its area. So it tries to minimize the area by making the domain walls flat. So that's the tension acting on the walls. This is always present. And now because we break the symmetry and lifted the degeneracy, the forced vacuum feels the negative pressure. And then this pressure is determined by the potential bias, here denoted by epsilon. And domain walls start to annihilate and decay when these two forces become comparable and this pressure due to the bias becomes dominant. So by equating these two forces, or just by equating the energy density domain walls with the potential bias, you can estimate when the domain was starts to annihilate. It's given by the Hubble parameter equal potential divided by the timing when domain will start to annihilate. Okay, so now let me go on to the gravitational wave production from domain wall decay. So domain wall annihilation is really a violent process. So it is a source of the gravitational waves. So this is just imagination of my imagination, and there's no actual explosion. So this should be interpreted as in a metaphorical way. But anyway, through this domain wall annihilation, lots of gravitational waves are expected to be produced. So the question is the spectrum of gravitational waves. And according to the numerical lattice calculations performed by these people, they found the gravitational wave spectrum given like this. So it is characterized by two parameters. One is peak frequency and the amount of gravitational waves at this peak frequency. And the dependence on the frequency is given like this. At the low frequency is given by f cubed, and at higher frequencies, it is inversely proportional to the frequency. And this f cubed dependence can be understood because this is nothing but the white noise power spectrum. So this f cubed dependence appears when there is no correlation at all. So it means that there's no correlation of the gravitational wave signals at frequencies lower than the peak frequency. This 1/f frequency is found in the numerical simulations, and there's no clear explanation why this should be 1/f. But anyway, this explains nicely the numerical results. So let us estimate the peak frequency, and it is quite easy. So let me do it slowly. So peak frequency is determined the typical the scale or typical the time scale for this process to happen. And the domain walls are curved, and the curvature scale is Hubble parameter, and also typical distance between domain walls is also given by the Hubble parameter. Everything is determined by Hubble parameter. So the peak frequency should be also roughly given by Hubble parameter at the time of annihilation. And after the production, so the gravitational waves are redshifted by the subsequent cosmological expansion. So you need to multiply the ratio of the scale factor. Then you get this value. If domain walls annihilate around the temperature of 100 MeV, the peak frequency is around 10 nanohertz. So by the way, the nanograph, one of the pulsar time array, the collaboration, the experiment, is sensitive to the about nanohertz. The most sensitive frequency is around 8 nanohertz. So there's some coincidence. And you can also estimate the peak height, namely the abundance of gravitational waves. So this is also easy. So you can just follow it just by looking at the equation here. So let me do it slowly. The energy of gravitational wave can be easily estimated by this formula that's just based on the Newtonian gravity. So G is a Newtonian constant. MdW denotes the mass of domain walls of that some volume. Here I'm considering the Hubble volume, and RH is a typical distance we are considering. Okay, and RH is nothing but Hubble radius because that's a typical length scale. And the mass of domain wall is estimated by multiply the domain wall energy density with Hubble volume. Okay? So you can evaluate energy of gravitation waves. Energy density of gravitation waves can be easily evaluated by dividing EGW by the Hubble volume. Okay? And because the energy density of gravitation waves is proportional to domain wall energy density squared, energy density of domain wall is proportional to tension. So the gravitation wave energy density is proportional to sigma squared. And the Newtonian constant is given by Planck mass, 8 pi times mp squared. Mp is reduced Planck mass, so this part is nothing but g. So if you count the dimension, sigma tension has mass dimension 3, because if you multiply it with area, you get energy. So this sigma square has mass dimension 6, m divided by m Planck squared. So this combination already has mass dimension 4. Okay, so the Hubble parameter appears everywhere, but they are canceled out in this expression. And now you can evaluate the density parameter of gravitation waves at the time of production, assuming that this can be estimated by dividing energy density of gravitation waves by the total energy density at that time. And this one, the denominator is given by 3h squared mp squared. So you get the energy density parameter for gravitation waves at the time of production is given by this formula. Okay? And again, after the production, the gravitational waves are diluted by the subsequent cosmic expansion. And so the current density parameter can be evaluated like this, because assuming that the universe was radiation dominated at the time of production, this density parameter can be regarded as fraction of the ratio of gravitational wave energy density to the radiation energy density. And this ratio is fixed apart from the slight change in the relativistic degrees of freedom. So roughly speaking, the current density parameter for gravitation waves can be evaluated by multiplying density parameter for current radiation, which is about 4 times 10 to the power 5. So this is how you can evaluate the current the density parameter for gravitation waves. They are given by a function of the tension and the Hubble parameter at the time of annihilation. And the peak frequency is nothing but Hubble parameter. Okay, you have to of course multiply this redshift factor. Okay, and the authors of this paper studied the evolution and decay of the domain walls on the lattice simulation, and they use this kind of Z2 model, and they introduce the delta V as a potential bias. This is auto function, so that's why this breaks the Z2 parity of the original potential. And then they estimated the gravitational wave spectrum for different sets of parameters shown by these dashed lines. So this, again, lower frequency has F cube dependence, higher frequency has F inverse dependence. Okay, and this fitting formula or some extension has been used in much of the literature on the gravitational wave production from domain walls. And as I mentioned, if the domain wall annihilation happens around the QCD scale, then the peak frequency happens to be around 10 nanohertz. And this is the range of frequency the PTA, pulsar timing array, are sensitive to. So the horizontal axis is the frequency in the units of hertz, and the y-axis is the characteristic strain. Strain is the dimensionless quantity that represents the amplitude of gravitational waves. So how much time is delayed, or how much space is stretched or squeezed. That is represented by this small number. So I took this figure from the nanograph paper in 2019, and at that time they had bound based on this nanograph 2018, and they expected to improve the bound like this. Anyway, the typical value is 10 to minus 15 or 10 to minus 16. It's very tiny value. So let me mention some caveat of the previous analysis. And I said in the paper I mentioned they solved the numerically the evolution of domain walls. However, they did not take account of the bias in the numerical code. Namely, they simply solved the equation motion for domain walls without potential bias. And then even without potential bias, domain walls continuously annihilate to follow the scaling solution. So gravitational waves are continuously produced even in this regime. And they stopped solving the numerical code at a certain point, and they estimated gravitational waves produced at that point. And so the bias is just used as a timing to evaluate the gravitational wave, assuming that domain walls annihilate instantaneously when the energy density domain walls becomes equal to the potential bias. Namely, when this equality is satisfied, they stopped calculating the numerical code and then evaluated gravitational waves at that point. So the reason why they adapted such simplification is that you can follow only the finite time in the numerical lattice simulations, and you have to make the domain walls to decay if you want to really see the decay of domain walls. But to this end, you need to add relatively large potential bias. Otherwise, domain walls does not decay. So you need to add large bias. But if you have large bias from the very beginning, the domain wall formation is affected significantly. And so ideally, we want to have the scaling solution first, then domain walls decay. But this is not possible in the case of the constant bias assumed here, because from the very beginning, the bias is large, and that affects domain wall formation. So domain wall network never reaches the scaling solution and just decay. So then you cannot evaluate gravitational waves correctly. So to circumvent this problem, they did not include potential bias in the numerical code, and it is just used as to evaluate the timing when we should evaluate the gravitational waves. That's and also the fitting formula, the peak position and amplitude and the frequency dependence is based on this numerical analysis without taking account of the potential bias in the code. Okay, so let me go on to the observations. The pulsars are magnetized neutron stars, and they are rotating very fast, and that rotation causes periodic observation of beams emitted from the magnetic poles, and they are really stable rotators, so they can be used as a very precise clock. For instance, the period of this particular pulsar is measured with about 12 digits of precision, so it's very precise. And so this figure shows the magnetized neutron star, and this red axis is the rotation axis, and in general, this rotation axis is misaligned with magnetic axis along which some radio waves are emitted. And because the neutron stars are rotating, so this causes an effect like lighthouse. So we observe pulses when beams swipes our line of sight. Okay. And because this rotation is very stable, they can be used as the clocks. And pulsar timing arrays, or PTA for short, is a set of millisecond pulsars that are observed over a very long period, like 10 years or 20 years, with time precision of 10 or 100 nanoseconds. And they look for correlated signatures in the arrival time of the pulses. And one of the targets is, of course, gravitational waves. So if gravitational waves pass through the solar system or our galaxy, that stretches or squeezes space-time. So if you measure the pulses from one pulsar, as gravitational waves passes through, some pulses arrives sooner, or some pulse arrives later because of this effect of the gravitational waves. So this can be thought of as the galactic scale gravitational wave detector. The typical distance to the pulsars used in this pulsar timing array is about 1 kiloparsec. But for your reference, the distance between the solar system and the galactic center is given by about 8 kiloparsec. And now the distance to the pulsars that are used in this analysis is about 1 kiloparsec. And now, probably to get a feeling, I also give another number. So let us estimate the sensitivity of the characteristic strain. As I said, the precision of pulsar timing measurement is about 10 or 100 nanoseconds, and they observe the pulsars over, say, 10 years. So actually, the recent the nanograph data based on 15-year observation, but let us take 10 years. Then the sensitivity can be estimated by taking the ratio. Okay, so if you divide by 100 nanoseconds by 10 years, you get 3 times 10 to the minus 16. So this gives the rough estimate of the precision of strain. And this number is close to the number of what I showed on a couple of slides before here. So it's close to the sensitivity of the nanograph data. Of course, there are lots of systematic effects, like the structure of neutron star could change sometimes, or there is also effect of the medium between the Earth and the pulsars. The pulsar has its peculiar velocity. Some pulsars also have form a binary, and so on and so forth. You have to take account all of those systematic effects, but you can guess the sensitivity roughly by this calculation. And you can look for the signal coming from gravitational waves, and to this end, you need to take angular correlation. Okay. Suppose that gravitational waves are coming from the back of the screen toward us or toward you, then the gravitational waves stretches and squeezes space-time like this. So it stretches along one direction and it squeezes along the orthogonal direction. This is how gravitational waves stretches and squeezes the space. So if you consider correlation of the timing residual, namely the delay of the pulses compared to the prediction. For instance, if you take correlation of the pulses near the zero angles, of course you get positive correlation. But if you take correlation of pulses separated by 180 degrees, you also get positive correlation because of this pattern. Okay. And on the other hand, if you take correlations of pulses coming from these pulses and this pulses separated by 90 degrees, then you expect to have negative correlation, okay, because of this quadruple distortion of space-time. And so this is what nanograph collaboration found. So this shows angular correlations of the pulses, and so y-x-axis the angles, and of course angle is close to zero, you get positive correlations, and also at the 180 degree separation, you also get positive correlations and negative correlations at 90 degrees. And this theoretical curve is called Hillingstone curve, and this is a characteristic pattern of the gravitational wave signal. And these points and error bars are the nanograph data, 15 years data, and it clearly shows the trend is consistent with this theoretical Eddington-Downs curve. So nanograph collaboration found solid evidence for gravitational waves at the frequency of nanohertz or 10 nanohertz. And one of the leading candidates for this stochastic gravitational waves in this frequency range is the supermassive black hole binaries. So galaxies contain such supermassive black hole binaries at its center, and the galaxies are known to merge and get bigger in the history of the universe. So supermassive black holes contain the galaxy will also merge, and before the coalescence, they are in the spiral phase and emit gravitational waves. And summing various contributions, there are many supermassive black hole binaries, and assuming they are isotropically distributed, you can estimate the amount of stochastic gravitational wave background generated by supermassive black hole binaries. And depending on certain models, you can explain the observed data like this. But it's also possible that there is some cosmological contribution to this stochastic gravitational wave background. And in fact, the fit of the predicted spectrum is not so perfect as far as the models of supermassive black hole binaries adapted in the paper of nanograph. So there is still room for other contributions. And so they also analyze possible contributions like this. So again, so y-axis, the vertical axis is gravitational wave abundance, or the omega GW, so density parameter of the gravitational waves, and x-axis is frequency from nanohertz, 10 nanohertz, and 100 nanohertz. And this gray region is the nanograph data. So this part shows non-zero value of gravitational waves. Okay. For some reason, they show their data in this violin-like shape. And they show that the many new physics model can explain the data, and including a domain wall contribution. A domain wall contribution is shown by this orangish line like this, and so this gives a very good fit to this nanograph data. So let me go on point to details of the modeling they adapted in the analysis. So based on the results of the numerical lattice simulation of domain walls, they adapted this kind of the gravitational wave spectrum for this domain wall, and this epsilon represents the this is not bias, but this represents the efficiency factor of gravitational emission. It's a Borda unity. This alpha psi is nothing but the density parameter at the time of annihilation, which we estimated on the previous slide. And this S function determines the form of gravitational wave spectrum. It has a bit complicated shape, but it contains three free parameters, but they fix A equals to 3, because if we at low frequency or at small x, this S of x is proportional to x to the power of A. And as I said, as long as we consider the white noise or there's no correlation at scales beyond the hyperhorizon, then A should be equal to 3. So they adapted this value, A equals set to be 3. And as I said that the frequency dependence at higher frequencies is given by 1 over f. And that corresponds to B equals to 1. But for some reason, they vary this parameter B from 0.5 to 1. And also C parameterize how this two regime changes from one to the other. So this C basically parameterize the shape of the potential, or how sharp the peak is. And they vary those parameters, namely the peak position, peak height, and the frequency dependence, and the, some peak shape. Then they get the best fit result. Okay, that's given by this orange line. Okay, so I think I explained the current status. Now let me go on to the recent work. So this work was in collaboration with Kitajima and Lee and Murai and Im. And the Kai Murai is a fresh postdoc at Tohoku University. And Lee, or Lee Junsok, so he is my graduate student. He actually performed all the largest numerical calculations of this work. Okay, so the model we considered is axion, and axion domain was coupled to QCD. So the potential of the axion is given by this. So M5 is the mass of the axion, F5 the decay constant as usual. And for this cosine type potential, you can analytically calculate the tension, and it's given by A times M5 F5 squared. And anyway, it is given by M5 F5 squared. This can be understood because potential height at phi equals 0 is given by M5 F5 squared. Width of domain walls is given by the inverse of the mass scale. So multiplying the energy density with width of domain walls, you get tension. And that's how you calculate the tension. And with this potential, we have multiple degenerate vacua. So if domain walls are formed, they are completely stable. Okay. So we couple phi to QCD to generate bias of the potential, namely to lift the degeneracy of the multiple vacua. So this is a potential we consider. So this coupling is really like the QCD axiom, but the difference is that phi field has a potential from other sources, and that potential is much larger. Okay, the potential coming from QCD just gives a slight difference in the potential energy at different vacuum. Anyway, coupling this axion to QCD like this, it acquires potential given by this. This is exactly the same as the QCD axiom. And as I explained yesterday, it is proportional to temperature-dependent prefactor topological susceptibility, chi of t. And chi of t is very small at high temperatures, but as temperature approaches QCD scale, it rapidly grows. The power is close to 8. So it's very rapidly grows. And when temperature is less than TQCD, 150 MeV, it becomes constant. Okay. So we have temperature-dependent bias in contrast to the previous analysis. So that's the main difference. So let me compare these two cases. In the previous analysis, or the analysis so far, they all assume the constant bias. Okay, so this x-axis is the temperature. Temperature decreases from left to right, and and then this black third line represents the energy density of domain walls following the scaling solution. Okay, so as time goes, energy density of domain walls decreases with time, and at a certain point, it becomes equal to the bias epsilon, and we define the T equality as a temperature when this equality is met. And after that, the bias, effective bias is significant, so domain will start to annihilate. And in the analysis so far, so everybody assumes that annihilation takes place instantaneously, and so domain walls disappear almost immediately after the T equality, and the gravitational waves are no longer produced after this point. This is how they estimated the shape of gravitational waves. Now, the situation is a bit different. So we are considering the axial domain walls coupled to QCD, and because of this non-perturbative effects of QCD, the bias is vanishingly small at high temperatures. Okay. So there's practically no bias at all at high temperatures. But as temperature approaches to the QCD scale, it starts to grow very rapidly. And at a certain point, again, it becomes equal to the energy density of domain walls following the scaling solution. And even after that, the potential bias continues to grow until it reaches to the constant value chi naught. So the actual evolution of energy density domain walls is given by like this. So when there's no bias, it follows the scaling solution. But once the bias becomes important, it starts to deviate from the scaling solution and then annihilate and in a finite time after T equality. And of course, gravitational waves are produced during these decay processes. And as a result, the peak frequency should be evaluated at the time when most of the domain was annihilated. And this is slightly later than the T equality. So the peak frequency is shifted to lower values in the setup, in the more realistic setup. And also, even after T equality, the potential bias continues to grow because of this temperature dependence. So energy density of domain wall system is now dominated by potential bias, not domain walls, but the potential bias inside the force vacuum. So energy configuration, spatial distribution is quite different from the ordinary case. In any case, because bias increases after T equality, energy density contained in the domain wall system increases. So does the gravitational waves. So in our case with temperature dependent bias, the peak frequency gets shifted to lower values, but peak height is enhanced. So that's the effect we expect. By the way, in the previous case with constant bias, if you vary the tension, the decay time also changes. But in our case, because there's no bias at all at high temperatures, there's for some range of the tension, domain walls always decay around the timing of QCD's phase transition. So it necessarily generates gravitational waves in the range of nanohertz or 10 nanohertz. And if you increase the tension too much, namely much larger than 100 TeV cubed, then actually the domain walls comes to dominate the universe after this point, because this bias is not very different from the total energy density of the universe at that time. So if sigma is greater than 100 TeV cubed, domain walls come to dominate universe, even eternal inflation could take place in the force vacuum. So this region will be excluded by the cosmological domain wall problem. But if sigma is close to 100 TeV cubed, the produced gravitational wave is so large that it may be searched for by the partial timing array. And what I have explained in the last two slides can be summarized by the equation as follows. So in the case of a constant bias and instantaneous decay, the peak position is determined by hyperparameter T equality, and the abundance at the peak frequency is estimated like this. I use the notation of this paper, but you can see that this part is exactly the same as the equation I derived before. And this epsilon parameter is again the efficiency parameter, which is over the 1, about 0.7. A represents the energy density of domain walls. So, and it's also over the 1. So we define the QUC parameter to take account of this uncertainty. And also I replace the energy density of domain walls with its bias because they are evaluated at the T equal T equality. Anyway, in this case, QUC parameter is over the 1. Now, in the case of temperature dependent bias, especially when you couple it to QCD, we expect peak frequencies shifted to lower values. And this can be taken into account by introducing coupling C or parameter C. And C is less than 1. So this represents how much the annihilation temperature is delayed compared to T equal T. And here I use the same parameterization, but we expect Xi parameter is much larger than 1 in this case. And now I show you the numerical results. So x-axis is the gravitational abundance density parameter of gravitational waves, and the x-axis, maybe I should show here, x-axis is the frequency, nanohertz, 10 nanohertz, and 100 nanohertz. And this blue band represents the results of nanograph analysis, where they use some the model based on the numerical results, and they varied 3 or 4 parameters to fit the data. And this the bound, one sigma, 2 sigma bound corresponds to the best fit. The corresponds is a result of numerical fitting to the data. And this red line is our numerical result. And you can see that it is consistent with this blue band. And also, this is enhanced compared to the semi-analytic estimate, namely based on the previous analysis with constant bias and instantaneous decay. The abundance is enhanced, and also peak is shifted to smaller values. Okay. So approximately the amplitude is enhanced by a factor of 20, and the frequency becomes half. And moreover, you can see that there is some bumpy features, and we believe that these are the real signatures, and they are physical because these features appear during the annihilation process of domain walls. And this gravitational wave emission during this annihilation process has not been taken into account in the previous analysis. So this effect is new, and this is a prediction of the domain wall in the scenario of the gravitational wave emission from domain wall decay. And these bumpy features may be searched for in the future analysis. Okay. And finally, these heavy axions that constitute the axion domain walls is coupled to QCD, so it can be searched for the accelerated experiments. Okay, and because we more or less fix the tension of the domain walls to explain nanograph data, so we fix some combination mass and decay constant, or more precisely, M5 F5 squared is given by some constant value. And this is shown by blue band. Okay. So this blue band is suggested by the nanograph data. And this dashed line represents the region which we expect to be explored by various experiments in future. So you can see that some of the parameters suggested by the nanograph data can be also explored by those the accelerated experiments. By the way, these regions are excluded by cosmological observations like BBN, CMB, and so on. Okay, so in the last 10 minutes or so, let me briefly mention the strong CP program in this setup. We introduced heavy axion and coupled to QCD. So the coupling to QCD is given by this. So phi is stabilized around the 0 or 2 pi f phi and so on. But at the potential minimum, the strong CP phase is non-zero in general. So the strong CP problem is not solved at this stage. So how do we solve the strong CP problem? So one simple solution is to introduce the QCD axiom, light QCD axiom. In this case, the QCD axiom, of course, starts oscillate when it feels the potential from QCD, but this should not take place too early, because once QCD axiom starts oscillate, the potential bias disappears. So in order for not to modify the change our scenario, the QCD axiom should not oscillate before the annihilation of domain walls. And this requires the axiom to be sufficiently light, or in terms of the decay constant, it should be greater than about 10 to 17 GeV. And for such large the axion decay constant, in order not to overproduce dark matter abundance, the initial misalignment angle of the QCD axion should be much smaller than 1. But this can be, of course, done by just fine-tuning. If you allow some amount of fine-tuning, this is always possible. But you can also dynamically explain this small value of initial misalignment angle by considering very low-scale inflation. As I explained yesterday, in the scenario of the stochastic axiom, you can dynamically explain a small value of theta I. So this is one way to solve strong CP problem. The other solution is to consider more complicated setup known as clockwork QCD axiom. The clockwork setup has been known for a long time. This is a nice generalization of the so-called Kim-Niels-Pelosso mechanism, where you can generate a very flat direction from the multiple axioms. And so let me explain how it works. Let me start with baby model with the number of PQ scalars equal to 2. So we have two complex scalars, phi1 and phi2. And we have two axioms, A1 and A2, so they are living in the phase of this exponential. Okay. And we consider relatively simple potential given by this. So in the first line, you have ordinary Mexican half-pipe potential. So phi1 and phi2 develops on the wave U1 symmetry. Each U1 symmetry gets pointed broken. And then axiom appears. But we also have this term, phi1 times phi2 cubed. So this explicitly breaks one combination of the two U1s. So initially we have two axioms, but because we have one explicit breaking terms, only one combination remains massless. The other becomes massive due to this explicit breaking terms. And this can be thought of as this kind of clockwork structure. So when the phi2 rotates by 2 pi, phi1 must rotate 3 times. So this kind of the structure is similar to the clockwork. So that's a name. That's the origin of this name. And you can see that the decay constant of the axiom corresponding to the lightest axiom is given by this equation. It's slightly enhanced compared to the original symmetry breaking scale, just by a factor of 3 in the case of n equal 2. But the situation changes significantly if you increase the number of PQ scalars. It's something like this. So if you have many PQ scalars with certain pattern of symmetry breakings, you can generate a large hierarchy between the decay constant corresponding to the lightest or massless axiom to the symmetry breaking scale here denoted by F. So it can be much larger than the actual symmetry breaking scale by a factor of 3 to the nth power. Okay. So this is the clockwork axiom model, and so we apply this the idea to the QCD axiom. And in particular, we considered the topological defects in this setup. Suppose that we have n PQ scalars, and they have so they are n U1s, and when this n U1 gets broken, we have n different type of cosmic strings. Okay, but after the symmetry breaking term becomes important, the domain walls appear, and so those strings are connected to each other by domain walls. But because of this very complicated structure, the topological defects network is very, very complicated. And that was first studied in this paper in collaboration with Professor Kwansik John at Kusan University. And the same, basically the same thing was also observed in this paper that appeared 2 years later by Andrew Long. And so but anyway, we have massless degrees of freedom, massless axiom, the QUC axiom, and the heavy axioms. And if you from the viewpoint of effective field theory, we can simply integrate out heavy axioms. Then we would have theory of massless or very light axiom. So we expect the configuration of the strings and walls that corresponds to the ordinary axionic strings. And in the case of n equal 2, this is the configuration. So we have cosmic string corresponding to phi 2, and it is connected to 3 phi 1 cosmic strings. This structure, this corresponds to the ordinary axion cosmic strings. In the case of n equals 3, we have 1 phi 3 string, 3 phi 2 strings, and 9 phi 1 strings, and so on. And you can imagine how it becomes complicated as you increase 20 to represent the ordinary axionic cosmic strings. So there is a configuration that corresponds to the ordinary cosmic strings, but it's a different problem whether this is really formed in the history of the universe. And actually, we believe it's very difficult because initially we have n different kinds of cosmic strings, and at the initial time they did not fill the breaking term. Those n different kinds of strings follow the scaling solution. Namely, we have one cosmic string of each type in the upper horizon. That's scaling solution. But in order to form this structure, by the way, which we call string bundle, we need exponential large hierarchy in the number density of different type of cosmic strings. And it to form from at all in the number densities, but form this you need in the different cosmic strings. And also run lattice simulation based on sorry, then the connection was unstable. Here, can you see and hear? Probably you can see my slide. And okay, so we run the simulation of the QUC axion with n equals 3, and at each time you have different kinds of strings and walls, and as time goes, some string bundles are formed, but still we have domain walls made of heavy axions. So this should be the case in the realistic case with a large number of n. So even at the time of QCD, we have domain walls made of heavy axions. So their energy density is very large, much larger than the ordinary the domain walls of QCD axion because tension is large. And so they annihilate at the time of QCD saturation because at that point the massless QCD axion acquires potential and it leaves all the potential the vacua. So the string wall network decay at the time of QCD saturation, producing gravitational waves in the nanohertz range. And if tension is about 100 dB cubed, you can look for the gravitational waves produced by this process, and heavy axion can be searched for as accelerated experiments. And this is exactly what we said in this paper 7 years ago. You can see the title that we mentioned that nanohertz gravitational waves can be produced by this clockwise QCD axion. So the axion domain wall coupled to QCD mentioned earlier in this talk can be thought of as the baby model of this clockwise QCD axion. Okay, so time is up, so let me wrap up my talk. So we considered axion domain walls coupled to gluons. Then in contrast to the previous, the cases studied in the previous the literature, the potential bias is time dependent and temperature dependent. And thanks to this temperature dependence, we could incorporate the the tension into our numerical lattice simulations. Because at each other time, there's no bias, so the domain robots have enough time to follow scaling solution and then decays due to this potential bias. And the produced gravitational waves have frequencies around nanohertz or 10 nanohertz, and this happens to be the sensitivity frequency of the PTA experiment. And we calculated the gravitational wave spectrum based on the lattice calculation and found that it nicely explains the data. The heavy axion can be searched for at accelerated experiments, and you can also consider a more complicated or realistic setup for this axion domain coupled to QCD. Okay, so that's all. So thank you very much for your attention.